Hi guys, this is the 8th of our 9 common techniques for rewriting integrands so that our basic anti-differentiation rules will apply. In this one we will be multiplying and dividing by e to the kx. Now I tend to use this when looking at an integral like this one. And just for the sake of comparison, I want to show you something very similar. So let's say we've got negative 3 over e to the let's say 6x, all divided by 1 plus 5 e to the 6x dx. And then for comparison, let's look at this one. For one of these, either my basic rule or u-substitution already applies, and for the other one, I'm going to need to use technique number 8. I'm going to multiply and divide by an exponential. Think about which one. Which one do I have a basic rule for? Well, first of all, I don't have a basic rule for either of them because I've got 2 terms in the denominator here, and I cannot split the denominator. It's not a possibility. So we can't split the denominator here, and we can't split the denominator here, so there are no basic rules that apply. Then for each of these problems, the next thing I would ask myself is, does u-substitution work? And it turns out that for this one, yes, u-substitution does work. Now remember, when you're choosing your u and u-substitution, you're looking for a function nested inside of another function. Usually there are parentheses around your u. U is inside an exponential function or inside a trigonometric function. Maybe u is under a radical. But usually there's some kind of grouping symbol just holding u together. In this case, one natural choice for u might be u equals 6x. But then after some manipulation, I'm going to end up with an e to the u down here times a 5 plus a 1. And there will also be an e to the u up here, potentially. So even though 6x is inside the exponential function, in order to avoid doing 2 u substitutions, I think I'd like to choose a different u. If I have 1 plus 5 e to the u down here, I'm going to have to substitute again. I'm going to have to substitute for the whole denominator. So rather than doing 2 u substitutions, or a u substitution and a double u substitution, what I'm going to do is let u be the denominator just to start. And this is actually going to work quite well. So I've got u here. That's 1 plus 5 e to the 6x. And then I compute its derivative. The derivative of 1 is 0. The derivative of 5 times this exponential is 5 times the derivative of e to the 6x, which is e to the 6x times the derivative of the inside. The inside has a 6 in it, so, does have a 6 in it, but the derivative of the inside is a 6, and we multiply by dx, so we end up with du equals 30 e to the 6x dx. Now I'm looking at this and I'm comparing it to this, and you have a couple of options in order to write this integral entirely in terms of u. I know that this will work because just ignoring the 30, I've got an e to the 6x dx there. If I have an e to the 6x dx as part of my integrand, as a factor in this integrand, then this is going to work. It's going to work just fine. That means I'll be able to replace e to the 6x dx with something times du. And I've got that. I've got an e to the 6x dx in the numerator. So that's going to work. Now, at this point, I've got 2 options for writing my integral in terms of u. Either I can take this equation and solve for e to the 6x dx, dividing both sides by 30, and then replace this e to the 6x dx with 1 over 30 du. That's one option. Or I can think about how to manipulate this so that when I'm done, I don't have a 30 times e to the 6x dx. I would really like to have a negative 3 times e to the 6x dx. If I want a negative 3 there, well, I can make that happen if I divide both sides by negative 10. So that's one possibility. I think what I'm going to do, rather than dividing by negative 10, to make it look exactly like the numerator that's there, I think I'm just going to solve for the e to the 6x dx this time. So we'll divide both sides by 30, and we have dividing by 30 is the same as multiplying by 1 over 30. 1 over 30 du is equal to e to the 6x dx. So now I'm going to rewrite my integral. I have the integral of something. This negative 3 is a constant. I'm going to factor that out. And according to this, according to what we just did, the e to the 6x dx, that's 1 over 30 times du. So I'm going to replace this by 1 over 30 du. So I have a 1 over 30 out front, and I factor my du off to the right. And I still have that u in the denominator. And it looks like that's it. We've done everything. Now remember that u was in the denominator. I can't just write a u in the numerator and say it's the same thing. So that u is in the denominator, and there has to be a 1 as a placeholder for the numerator. So at this point, I can just anti-differentiate with respect to u, simplify my coefficient, and then back substitute. So negative 3 over 30 reduces to negative 1/10. Then we take the natural log with the absolute value of u plus c as our antiderivative. And then we replace u with whatever u was in terms of x. And u was this 1 plus 5 e to the 6x. So we're going to substitute that in. And that would be fine. We would be finished. But if you check your answer in the back of the book, this function is always positive because exponentials are always positive. If I multiply by 5, it's still positive. If I add 1 to a positive number, it's still positive. So if I'm checking my answer in the back of the book, what I might see is negative 1/10, natural log of 1 plus 5 e to the 6x plus c. And we're done. All right, so we're done with that. Now that worked. Why? Why did that work? The u-substitution worked because when I took the derivative of the denominator, notice I had a constant times e to the 6x. The e to the 6x down here, when I took its derivative, it came back. There was another e to the 6x. It had to be in the numerator as well. Since I had a matching exponential in the numerator and denominator, this is u, and that's a constant times du up there. And so we were able to do the u-sub. Now let's look at this one. Are we going to be able to do the same u-sub? Now we're going to have a problem because I don't have a matching exponential in the numerator and denominator. So if I let u equal this, and I calculate du equals 30 times e to the 6x dx, I'm not going to have the e to the 6x dx that I need in order to complete the u-sub. So this is where we're going to use our 8th technique, multiplying and dividing by e to the kx. We do this whenever it looks kind of like one of these, but the u-sub's not already set up for us. I've got an exponential down here, but not a matching exponential in the numerator. So we rewrite it. I've got a negative 3 in the numerator over 1 plus 5 e to the 6x. Now, in order to get the matching exponentials that we want, this is what we do. You see that e to the 6x? I'm going to multiply by almost exactly the same exponential, but instead of an e to the 6x, I'm going to write that as e to the negative 6x. Whatever that is, it's going to be the same exponential, but with the opposite sign. So I have a 6x here, I'll have a negative 6x there. And remember, whatever you do to the denominator, you've got to do to the numerator as well. That way we're just multiplying by a well-chosen 1. Multiplying by 1 doesn't change anything, it just changes the form of the expression that we're looking at. So I've got a negative 3 times e to the negative 6x. And be careful in the denominator, you have to distribute. You've got 1 times that exponential plus 5 e to the 6x times that exponential. 1 times an exponential is itself. And then watch what happens here. I have 5 times 1 is 5, and e to the 6x times e to the negative 6x. Remember, when we're multiplying exponents, if they have the same base, we add the exponents. 6x plus negative 6x is just e to the 0, and e to the 0 is 1. So we're here now. By multiplying by that e to the kx, look what we've done. We took a problem where u sub wouldn't work, and because this times this was just a 1, and then we distributed that to this other one, we created a problem where the u sub does work. I've got matching exponentials now. I've got an e to the negative 6x down here, and I've got the same thing in the numerator. So this is going to work out just fine. We're going to be able to do the u sub after we've multiplied by e to the kx over itself in just the right way so that these two guys cancel and we're left with this. I can do the u sub and u is my denominator. It's going to look very similar to this problem that we have already solved here on the left. So let u equal e to the negative 6x plus 5. Compute the derivative. Remember, the derivative of e to some power is e to that power times the derivative of the inside by the chain rule. And the derivative of negative 6x is negative 6. Multiply by dx. Now at this point, I have options. I can either take this and manipulate it. I can multiply or divide by something so that when I'm done, I'm left with a negative 3 e to the negative 6x dx over here. Or I can just divide both sides by negative 6 and replace the e to the negative 6x dx with negative 1/6 du. That's what I did over here. I'm going to try it the other way for this one, just to show you that you can do it either way and you're going to get an equivalent answer. So I want this to be a negative 3. I've got a negative 6, so I'm going to divide both sides by 2. And I end up with 1/2 du equals negative 3 e to the negative 6x dx. All right, so now I want to write everything in terms of u. This negative 3 e to the negative 6x dx, that is 1/2 du. So I'm going to write that as a 1/2 out front and a du off to the far right. And that, remember, is a u, but it's in the denominator. And there's nothing else in the numerator, but I can't just leave it blank. We've got to put a 1 in as a placeholder. 1/2 times 1 over u, that's a 1 over 2u if I simplified it, times du. If I plugged in u and I plugged in du and I simplified everything, it would be equivalent to this up here. I'm not going to prove that right now, but you can check it. You can pause the video and check it if you like. This is truly equivalent to this. And then I ask myself, do I now have a rule for that? And absolutely I do. I've got the 1 over x rule. We know the antiderivative of 1 over x is natural log of the absolute value of x plus c. It's just a u instead of an x, no big deal. So I've got 1/2 of natural log of the absolute value of u plus c. U is this. And then u turns out to be e to the negative 6x plus 5. Just so happens this time this is a positive function. It's always positive, it's always greater than 0. Then I add 5 to it, and then it's always greater than 5. So I don't really need the absolute value bars. You can stop here for a quiz or a test. You'll be good to go. Or, oops, you can write it this way. Since that number is always positive, I don't really need the absolute value. And I don't know why I put the 5 out front, just seemed to fit a little better that time. I like the way it looked. There we go. And that's our 8th technique, multiplying and dividing by e to the kx.